This video is part of a course on food physics, of which this belongs to the applications section. It is on puffing and it with rice puffing as an example. It is the last or part 4 of the 4-part video on puffing. So here we are going to take a quick look at several other processes where the puffing physics that we discussed in the last 3 videos of this series might apply or might have commonality. We're just going to look at these processes. Now, of course, we're not getting into details of these processes. Some of them have their own videos. For example, for bread baking, we have or we will have a video on dedicated to just bread baking. So we're not going to get into that much details. And at the end of this video, we're going to summarize all the 4 parts. So bread baking is not something we normally think of as puffing, but of course, starting from the dough, when it becomes the bread, it of course has puffed up. It has increased the volume. So let's look at it little more detail. And as the temperature increases, we have more CO2 generation, pressure increases, there is more evaporation with increased temperature. So the water vapor plus CO2 produces the pressure, and that makes the dough expand. Simultaneously, at the higher temperature, there's more moisture loss, and the outer dried layer or the crust is formed that has reduced vapor permeability, and that causes further pressure release. And so finally we have the shape because it dries up and retains the shape as this new material. Okay, so how does it relate to rice puffing? Let's look at that. What's the similarity? So there's significant gas phase production, that's vapor plus CO2, faster than it can be released. The crust formation helps in reducing the release rate. So this leads to higher pressure when the material is still soft, and this leads to expansion, and simultaneous drawing and change of material sets the final shape. So those are the same kind of processes that happened in rice puffing. Another example can be extrusion puffing, where you have the material coming out. So let's say, and the material, the molten material comes out and it puffs. Okay, and so in this extrusion puffing also we have similarity, but let's look at the process first. So high temperature and pressure of the melt. So this is my melt, and because the entire thing is being pressurized, so it is at a higher pressure and also at a higher temperature, so the material is soft, and then sudden change of pressure here, sudden change of pressure, and so now there is fast evaporation, and that causes higher pressure generation. As the outside pressure is released, then water finds it easier to get evaporated. So this evaporation causes pressure generation. So this pressure gradient this way and this way causes the generation here. Pressure gradient this way and this way causes pressure expansion, and simultaneously there is also loss of moisture due to evaporation and also of course diffusion of moisture. And as it's drying out, as the material is drying out, it's going from it's becoming hard and retaining the shape. So again, how does it relate to rice puffing? So there's large pressure gradient. Again, this large pressure gradient as it just comes out of the extruder when the material is still soft. So remember, in rice also we had this large pressure gradient formed when the material was soft. So that leads to expansion, and then simultaneous drying and change of the material. So material change becomes more glassy and hard, so that sets the final shape. So again, they are similar. Yet another example is microwave puffing that can be used to produce snacks without frying and therefore generally with less oil. So here is an example of a dough puffed in home microwave oven. Details of this can be seen in this paper. So let's look at this process in detail first, and then we will see how it shares some of the physics with the rice puffing. And so first we take the dough and we shape it, we roll it, and so then we do this blanching and slightly drying. Why? So that the surface permeability is reduced. The surface is made more impermeable. This is to contain the vapor. This is to increase the pressure inside. So then we put it in the microwave. So when we put it in the microwave, then we have this rapid temperature increase and rapid internal evaporation. And so that is going to cause pressure generation because the vapor is being produced faster than it can leave, and that's because the surfaces have been made impermeable or somewhat impermeable, and so then the material though is not completely dried up. It's not too, and therefore it's not too hard or too soft at the right moisture content, and that causes it to puff. The pressure inside and the pressure gradient from inside to the outside causes it to puff. So how does it relate to rice puffing? So microwaves lead to faster gas generation. That's the water vapor generation, faster than it can be released. And the crust formation helps in reducing the release rate. This leads to higher pressure when the material is still soft, and that leads to expansion, and the simultaneous drying of the material and the change of the material to becoming more glassy sets the final shape. So again, you see the parallel between rice puffing and this one, that you're generating pressure faster than it can go out at a time when the material is soft. That's what leads to puffing. So to summarize the 4 videos in this series on puffing with rice puffing as the primary example, let's go over the basic facts or ideas of a puffing process. So first thing is many changes happen in a short time. Puffing is a rapid process and many things happen in that short time. Then the sequence goes something like this. As you heat the material, the temperature rises, and the increase in temperature softens the material. So if it were glassy, hard, it becomes more rubbery, that can be changed more easily. Simultaneously, there is evaporation of water or vapor generation. That's the gas that causes the and if that vapor generation is faster, then it can be released through the surfaces. Then the pressure develops, pressure rises inside, and this increased pressure expands the material. That is puffing. Now, as it expands, the material also dries and it kind of hardens. It goes from rubbery to glassy state, and that allows the puffed shape to be retained. So whatever the increase in size was, it is retained because it's now dry and hard. In terms of the factors that affect the final puffed volume, of course there are many, but we just looked at 2 of them. One was temperature and one was moisture. So too low a moisture and too high moisture, they both lead to lower puffed volume, and that we discussed some of the reasons for that it is not great to have very high moisture. So to get high puffed volume, then we have high temperature. Higher temperature gives higher puffed volume. The optimum moisture, not too low, not too high. And then in case of systems like gun puffing, where we are suddenly able to make a pressure change to really increase the puffed volume, the faster the pressure release, the greater is the puffed volume. So fast pressure release in pressurized system would also give large puffed volume. Now, much of the basic physics that we discussed for puffing in the particular example of rice puffing applies to other processes that we may or may not call as puffing. So here we have 3 examples of bread baking, extrusion puffing, and microwave puffing. So in each case, you see the material needs to be softened, if not already soft. And then the rate of gas generation inside, so rate of gas generation inside has to substantially exceed the rate at which the gas can escape. Now that can be done in 2 ways. One is by forming a crust that kind of impedes the gas flow out, or just by increasing the amount of gas generation, as would be done by the yeast in this case and the CO2 formation. By gas, I mean either CO2 or the water vapor. We just need a gas inside that kind of pushes things out. So that causes it to expand, but the simultaneous drawing of the material and the material changing to a harder form kind of arrests the shape. So that physics is shared by the three examples shown here. Now let's generalize further. I want you to see that this was one of the application videos. So it was more about rice puffing, but then we generalize the physics that we learned into other puffing processes. So it's much more broadly applicable. But it's actually even more broadly applicable because there are other processes that share a part of the physics. For example, in microwave drying, we'll have some of the same physics happening. So what we learned here is not just useful for rice puffing or even just puffing. It's beyond that. It should help us to understand and optimize in terms of many different food processes and understanding food processes where heating is involved. Now, a few comments about moving beyond this particular set of videos on puffing or rice puffing. In the big picture of food physics, an application such as puffing, scientific understanding and optimization of it really sits on a three-legged stool, and the legs being the theory or the framework that of the physics that provides us with a way to track all the different phenomena that is happening simultaneously. Then from the theory we develop modeling and simulation, or from the understanding of the theory we design experiment, or we do modeling and simulation and validate the simulation results with experiments. Either way, experimentation is also a critical part. If the underlying animations that you saw in these videos is of interest to you, and the physics behind those models that led to the animations, then you should look into the set of modules under theory, and if you have interest in modeling and simulation, then you should look at the set of videos under modeling and simulation. All that is just part of having an improved understanding of the food physics. Thank you.